All right, let's get right into it. Today we are going to pull back the curtain on two really popular machine learning algorithms for classifying text, Bernoulli and multinomial naive Bayes. We're going to break down what they are, how they're different, and most importantly, when you should use one over the other.
You ever stop and wonder how, like an app on your phone can instantly tell if a movie review is a glowing recommendation or a total PAM? That magic is a classic problem called sentiment analysis. And to make it work, you need data. A lot of data. We're talking about huge data sets like Stanford's, which has something like 25,000 movie reviews just for the training part alone.
So the fundamental challenge here is actually pretty easy to describe, but way harder to solve. We have to teach a computer how to read and understand human emotion. I mean, think about it. We're taking all this messy, unstructured text, whether it's a review, a spam email, a tweet, and we have to turn it into nice, clean, structured data that an algorithm can actually understand and learn from. So how in the world do we tackle that? Well, one of the most popular and, believe it or not, powerful ways to do it is with a family of algorithms called naive Bayes classifiers. They're super fast, they're really effective, and honestly, they're a fantastic starting point for almost any text-based problem.
Okay, the key to understanding this whole thing is right there in the name, naive, and it's called that because it makes this massive and, let's be honest, completely wrong assumption. It assumes that every single word in a sentence has absolutely nothing to do with any other word. It pretends that in the phrase, great movie, the word great has no connection to the word movie. Now, we know that's just not how language works, right? But making this naive leap makes the math behind it so much simpler.
And here's the really wild part. Just like this quote says, even though that core assumption is fundamentally wrong, these classifiers work shockingly well out in the real world. And that paradox, that's what makes them so cool. So let's see how that's even possible.
All right, so naive Bayes isn't just one single algorithm. It's more like a family. And within that family, there are different models. Let's kick things off with the first one, the Bernoulli model. This is one particular way to read and interpret a sentence. The easiest way to think about the Bernoulli model is to picture a simple checklist. For every single word that it knows about in its vocabulary, it just asks one question. Is this word anywhere in the document? It's a simple yes or no, a 1 or a 0. It could not care less if the word appears 1 time or 100 times. Just, is it there? Let's make this concrete. Take the sentence, I love this movie. Now pay close attention to the word movie. It's in there twice. But look at what the Bernoulli model does. Since it's just a checklist, it sees the word movie as present and it just puts a 1 next to it. That's it. It completely ignores the repetition. It's all about simple presence versus absence.
Okay, so that's one way to look at a sentence. But now, let's put on a totally different pair of glasses and look at that exact same sentence through the eyes of the multinomial model. It has a completely different philosophy.
So if the Bernoulli model was a simple checklist, the multinomial model is a tally counter. It's not just asking if a word is there, oh no. It's asking, okay, but how many times is it there? It keeps a running tally, tracking the frequency of every single word. And boom, here's the difference in black and white. Same exact sentence, I love this movie. But now look at the table. The multinomial model has put a 2 next to the word movie. It actually captured that repetition. And that can be a really powerful piece of information, right? The fact that someone said movie twice might actually mean something. So we've got our two main players, the checklist and the tally counter. And this brings us to the big question. How do you know which tool to pull out of the toolbox for your project? Let's put them head to head. This really lays it all out. Bernoulli is purely binary, 1 or 0, yes or no. Its entire focus is just on whether a word is present or absent. Multinomial, on the other hand, deals in frequency counts. It's all about how often words show up, which means, crucially, it cares about repetition. So, why would you ever pick Bernoulli? Well, for one, it's incredibly fast and simple to calculate. It's especially good for really short bits of text, like tweets, where a word probably isn't going to be repeated much anyway. And here's a neat trick. It actually treats the absence of a word as a feature, which can sometimes be a really useful signal. But then you have the multinomial model. And a lot of the time, this one actually gives you better accuracy. Why? Because it's using more information. That word frequency tells you something about emphasis and importance. This makes it a much better fit for longer documents, like articles or those movie reviews we started with.
So here's the bottom line. It really just comes down to your data.
If you're working with short stuff like tweets or text messages, Bernoulli is a fantastic lightweight choice. But for longer documents or any situation where you think word repetition really matters, like in a passionate movie review, multinomial is almost always going to be the way to go. So let's bring this all home and get back to that central mystery we talked about. Why on earth is a model built on a naive, fundamentally incorrect assumption so ridiculously effective?
It all comes down to being good enough. That naive assumption that all words are independent, it just makes the math so much easier. This lets naive Bayes models train at lightning speed, and they often work great even without a ton of data. The thing is, for a task like deciding if a review is positive or negative, the model doesn't have to get the exact probability perfect. It just has to figure out that the probability of positive is higher than the probability of negative. And for that, this simple, naive approach works beautifully.
And that's really the final thought to leave you with. In a world where AI is getting more and more complicated, the wild success of naive Bayes is this awesome reminder that sometimes the simple, fast, and elegant solution is actually more useful than the one that's theoretically perfect. It's a perfect example of practical engineering triumphing over pure theory.